Hey guys, today we're going to talk a little bit about projection, force, and work. So this is going to feel really physicsy, so just take an adventure with me and we'll see if we can figure it out together. So the first thing that we need to figure out is, first of all, what the heck is projection? So no, projection is not if you're angry, acting like everybody around you is also angry. That's not the same kind of projection. The projection of one vector onto another, so the projection of maybe vector u, I should put the of there, of vector u onto vector v is going to have this formula. So this formula we're going to need, try to make it loud and proud. So my projection onto v, u is going to be the dot product of u and v divided by the magnitude of v squared. And that's going to give you a scalar. So then whatever that scalar is, you're going to multiply it and distribute it out onto that vector v. So right now you might be sitting there thinking, okay, great, what a nice formula, but what in the heck does that mean? So it's a little bit confusing, at least to me. So if this makes perfect sense to you, I would love to see what you have to say, and I would love your explanation. But here's how I was kind of taught to think about it. The projection of one vector onto another is kind of the shadow of one vector onto another. So it's kind of the shadow of u onto v. So let me draw you a picture so I can show you exactly what I mean. So maybe I have a little coordinate plane right here. And I will have my vector v right here. There's my vector v. All right. And then I'll have my vector u. Maybe he will be up here somewhere. He is vector u. So the shadow, now if we were to think about like a light source, like, you know, maybe there's the sun coming in and it's going to be perpendicular to that vector v. So if we think about it that way, it's going to come and u is going to make a shadow down here onto v, and that is where the projection of u onto v is going to be. So basically I'm going to be in the direction of v, but still have the magnitude of u. So it's going to be a little bit different. So another way to think about it, it is how much of u goes on v. How much of vector u goes onto v. So that's pretty much what we're talking about. And then force and work, we are going to have to use... Sorry about that. I just had to pause for a second because a kid came in and I have no idea what I was just saying. So for you, that was just a stop, and then I just started talking again. But for me, it was like a long break. So anyways, how much of u goes onto the v direction? So let's go ahead. We're going to use that for both work, or force and work. So first, let's take a look at an example of just doing a projection without any sort of application to it. So we're going to do a couple of these just to get used to it. If you need to skip forward because the first example was enough and you don't want to see the second one, go right ahead. It's all you. So we are going to find the projection of u onto v. Now remember, sometimes we're going to have these little hats on our vectors, sometimes they're bold. I just want you to get used to seeing them in different ways so that way you're not afraid when you see something a little bit different. So our first example, I'm going to project u, which is 3, -5, onto vector v, which is 6, 2. So remember our formula for this guy, our projection onto v of u equals the dot product of u and v divided by the magnitude of v squared. And then once we get that scalar, we're going to distribute it through that vector v. So that way we can keep the direction of that vector v. So the first thing we want to do is we want to find our dot product. So I'm going to find u dot v. And when I find u dot v, I'm going to end up taking 3 times 6 plus -5 times 2. So that leaves me with 18 minus 10, so my dot product is going to equal 8. The next thing that I'm supposed to find is my magnitude of v. So we've been finding magnitude for a long time, so I'm going to end up with 6 squared plus 2 squared, and then we'll square root that sucker. So 36 plus 4, so I end up with the square root of 40. So now we will pile this into our formula. So I want the projection onto v of u. So the dot product goes in my numerator, so I'm going to have 8 divided by the magnitude squared, so square root of 40 squared. And then once I get that guy, I'm going to distribute that number out along my vector v. So vector v is 6, 2. All right, so when I square a square root, they're just going to cancel out. So I have 8 over 40, and I'm going to distribute him out over 6, 2. So he's going to kerplunk, kerplunk. So I'm going to end up with, once I distribute out, let's see, 48 over 40 and 16 over 40. Those can easily be cleaned up, so go ahead and simplify them. We'll end up with 6 fifths and 2 fifths. So that guy right there, that's going to be my projection of u onto v. That is the magnitude of v. It's like kind of the shadow of v. I'm sorry, the shadow of u onto v right there. So I'll have the direction of v. So let's look at another example. So b, my vector u is going to be -5 or -1, and v is going to be -1, 1. So remember, my projection onto v of u is going to be my dot product of u and v divided by the magnitude of v squared, and then I'm going to distribute that scalar out along my vector v. So the first thing we're going to need to do is go ahead and find our dot product. So we're going to find u dot v. So to find the dot product, I'm going to have -5 times -1 plus -1 times 1. Oops. There we go. So let's see, that makes +5 plus -1 gives me 4 for my dot product. Then we'll go ahead and find that magnitude of v. So I'm going to take -1 and square it, plus the other one and square it, square root that sucker. So I'll end up with the square root of 2 after I simplify that. So then we just pop it all into that formula. So the projection of onto v of u is going to be my dot product up on top. So I'm going to have 4 over the magnitude of v squared, so the square root of 2 squared. And then once I get an answer there, I'm going to distribute it out through my v vector, which is -1, 1. So here's what we know over here. We have 4 over, And then I have the square root of 2 squared, so that's just 2. 4 divided by 2 is, oh man, 2. So I know I've got a 2 out front, and I'll distribute him through that vector v right there. And I will end up with negative 2, 2 for my projection of u onto v. Now, that is how we find a projection. But why would we want to? What's the use of it? So the next thing we're going to look at is we are going to look at force. Now, if you want a better explanation of what force is, I'm sure there is a physics teacher that would love to give you the ins and outs of it. I just don't think I have that expertise. So force is essentially something that changes the motion of an object. So I think the best thing to do is to jump straight in with an example, so that way it might be a little bit easier to see. So here we go. A 200-pound cart sits on a ramp inclined at 30 degrees. What force is required to keep the cart from rolling down? Okay. So here's what I think is a good idea to do. Go ahead and draw a picture. So first of all, there is the ground. And then there is a ramp. And he is coming up at 30 degrees. And on top of that is a cart. So I will do my best to draw a little cart here. There it is. Isn't it cute? All right. So let's first talk about this cart. Now, we know how gravity works. With gravity, the Earth is pulling things toward it. So this cart is being pulled straight down to Earth. Are we cool with that? It's being pulled straight down. So let's write a vector for the wagon. So since he is going straight down, there is no horizontal part of my component. And then since it's all going down, that entire magnitude is going to be going in the negative vertical direction. So that means that this part is going to have to be negative 200. Now, maybe that didn't make any sense whatsoever. Let's go back and think about the unit circle for a second. Here's 0, here's 90 degrees, here's 180, here's 270. Now, if we have a vector that is being pulled straight down, that is in the direction of 270. So let's say we want to use 270 as our direction angle. We totally could. So I'm just going to go ahead and do this over here. Here's another way to think about it. So the magnitude is 200 times the cosine of 270, and then for my vertical part, 200 times the sine of 270. And if you go ahead and work that out, the cosine of 270 is 0, so that's why I end up with 0 in my horizontal component. And then 200 times the sine of 270 is going to be negative 200. So that's why I get negative 200 in the vertical component. So whichever way you want to think about it that makes the most sense to you, I am on board. Now let's talk about the ramp. So the ramp doesn't have any magnitude, but we definitely have direction. So let's make a magnitude given direction. So I'm going to end up with the cosine of that direction is 30 degrees. Sine of 30 degrees. Now, because you know the unit circle, you should not have to run to your calculator for this. The cosine at 30 degrees is going to be the square root of 3 over 2. The sine at 30 degrees is going to be 1/2. All right. So if you notice, remember how we were talking about how we have these lines that are it's pulling the cart down to the earth. So it's kind of like we were looking at a second ago. I'm going to hop back. It's kind of like how we were looking a second ago. Those beams of light were making that shadow of U onto V, right? Well, this time it's that gravity that's pulling that cart onto my ramp. So I'm going to want to project my cart onto the ramp. So I need the projection of the, am I calling it a cart or a wagon? Let's call it a cart. You're probably going to be mad at me that I'm now changing this word to cart instead of wagon, but okay, cart. So I'm projecting my cart onto the ramp. I'm sorry. I'm projecting my cart onto the ramp. So I'm going to have to dot these two vectors, divide it by the magnitude of that ramp vector squared, and then I will get that constant and distribute it out over my ramp vector. So here's a few things we have to find. We have to find R dot C. So we have to dot my ramp and my cart vector together. So when I dot them, I'm going to end up with 0 times square root of 3 over 2 plus, let's see, negative 200 times 1/2. So let's see, I got 0 plus negative 100 is negative 100 for that dot product. Then we need to have the magnitude of R. You can definitely go through the math of take those two components, square them, and then add them together. But also we should know that's the same sort of triangle that's made on the unit circle, and the hypotenuse of each and every triangle on that unit circle is going to be 1. So the magnitude of my ramp vector is going to be 1. So let's go ahead and plug that all into our formula. I'm sorry, I have to change. There we go. So when I project onto the ramp, my cart, so I've got negative 100 on top over, my magnitude is 1, and then I'll square it. And then once I simplify that, I will distribute through on my ramp vector, which is square root 3 over 2, 1/2. So 1 squared is 1. Negative 100 divided by 1 is negative 100. And then I've got, still inside the square root 3 over 2, 1/2. So after I simplify, I'll end up with negative 50 square root 3, and then negative 50. And here's the vector that we end up with of that cart being projected onto our ramp. But that's a vector, right? We kind of expect, what force do I need? It kind of sounds like it's supposed to be a scalar. And you're right. So to find the force, we are going to take the magnitude of him. So I'm going to have one big square root. I've got negative 50 square root 3. And I'll square him plus negative 50, and I'll square him. So then when I throw that all into my calculator, believe it or not, that's going to end up being 100. So what is the force that is needed to stop that cart from rolling down the hill? The force needed is 100 pounds. So we need 100 pounds of force to get that thing to not move.